Thank you, Georgi. I'd like to start with a little video. I don't know if I'm going to be successful with this, but so So, since we don't have a loudspeaker, I'll just do the speaking to this. OpenSPL has the whole concept of computing in space, and what this little video is trying to show is that it relates to really computing in a similar fashion as you do in an assembly line or in a factory, where the data flows through and you have these operators that are pushing and doing something to the data. And contrasting it with temporal programming, which is what you've been hearing about so far today, which is programming sequences of actions that are happening on cores, on state machines, on communicating sequential processes. So here, this is the split of the computation into a control and the data stream, which is, of course, the opposite of regular programming, where you build objects to connect the control and the data together. So once you've split it, you can basically create an infrastructure on the space of the chip, and you flow the data through the whole thing. And as the data flows through, computation is not the main thing. Computation is a side effect. It's just something that also happens as the data flows through the chip. What you've described is the flow of data. What happens as a side effect is your computation. And so that's kind of the core essence, and we've decided to put together a consortium that is driving that new way of doing computations. And so, having started with this, maybe going a little bit back to the history, how did we get to such a completely insane point of activity? So, I like to start with a little quote, because really I'm trying to set up a kind of jump from what we've heard so far in terms of how do we make more and more cores work for us, more and more different cores, more and more instruction streams and threads work together in a heterogeneous environment, and go over to a different problem, which is how can we use space on silicon in order to do computation? And that's a whole other story. The reason why this is interesting from a perspective of this particular session is that we do have FPGAs out there that give us space. And they don't tell us what it is that we need to do with that space. They just give us silicon area and say, you can program this, do something. Right? And I like to step back and say, what is it that we would like to do, assuming that the space is going to increase? We can see that there is no limit to how much more space we could have, while we do know that we've hit all of the limits of time. And so that's why there is this different concept of space. A few examples of what we've accomplished so far. So this shows of course, one particular top supercomputer list. This is an old one from November 2013, but there's not much exciting stuff going on here. And add a little quote here, where at the ASCLOS conference in 2014, somebody dared to say that specialized architectures, languages, and system software should largely supplant general purpose alternatives within the next decade. So that's all very exciting for us. This means that sitting here is really the right thing to do, and we should just look at what can be done. So here's an interesting example of something that we can do once we step away from the microprocessor. And one thing you can do is you can start to solve really large problems like partial differential equations. This is a shallow water equation, part of a weather model. And this is work that was done over in China at Tsinghua University by a student in the Geosciences Computing Joint Center of Computation. And then he did a little project and he figured out that by laying out his algorithm in space, he can get the following advantage over a Tianhe 1A node. And so, as you know, this is a GPU-based node. It's fairly compact. It was optimized to be a very, very large machine. And nevertheless, a student in a little project, transforming the code to a different paradigm, to a different way of computing, managed to get a 14x improvement in terms of speed and a 9x improvement in terms of power. So this is a fairly significant and substantial improvement done by a little project compared to a leading supercomputer. And yet at the same time, because this is such a different compute paradigm, there is no chance that this technology would ever enter any top supercomputer list in the world, right? Because simply the measurements are done completely differently and it wouldn't ever actually show up. There is a different bit here, which was done at Oxford. So this is work at the Applied Mathematics group in Oxford, which was looking at what kind of arithmetic, what kind of representations for the data is really necessary in order to do these early computations. And they found out that they could use 15 bits for 98% of the computation of the weather model, which is quite staggering, right? Because we know that nobody is allowed to compute weather anywhere in the world without double precision plotting. If you talk to anyone, anywhere, they say you simply cannot calculate weather computations without double precision plotting. And yet, if you study the actual math, in 98% of the time, it's all good. Of course, the 2% of the time, you do need to use float. And that's okay as well. So looking at heterogeneity, you can look at heterogeneity in types of hardware, but you can also look at heterogeneity in terms of how data is being represented, how the arithmetic is being done. And so putting all of these things together, this is an actual Dataflow-based machine standing next to an IBM Blue Gene here, which has just been installed by the UK government and is actually available to companies and to universities in the UK for studying a variety of different algorithms. So there is a kind of transition from research ideas over to actually solving real-world problems, having an impact, and doing something that makes a difference out there in real application areas. Now, of course, one of the key challenges that we have out there is the power challenge. And so if we look at the core of computation, you have, let's say, double precision floating point, which I'm told today would take about 100 picojoules. And it will go down to 10 picojoules in the future. Of course, moving data on the chip for 1 millimeter, moving it for 20 millimeters costs energy. So while we know that we can compute fairly cheaply, transistors are getting smaller and smaller, arithmetic is getting cheaper and cheaper, moving the data on the chip still remains the same. So today, 2020, is still 6 picojoules. It's not going to get any better. If you want to move that data across the chip, you don't have to pay for that. And it's not going to cost you any energy at all if you push this further out to do the computation. All of the energy is going to be spent moving the data. And yet, your computer program doesn't explicitly say how you need to move the data, so you can't optimize it as a program. Right? So in computing in space, you're describing the movement of data, which is the thing that actually takes the energy. And that gives the programmer the opportunity to actually describe the optimization he wants to do. He wants to minimize the movement of data. He wants to put this here, put this there, then move it here, move it there. And that's not the way programmers think. It's very, very unattractive. Because programmers are educated to think in terms of do this, do that, do that, do this, and the data will just be there. Right? So it's a kind of turning everything upside down. Moving data off chip, of course, that's kind of a disaster as well. to be avoided at all costs. So moving data on chip will use as much energy as the computation. Moving data off chip will use 200 times more energy. So it will be a lot cheaper to compute 10 times more than to move even twice as much. Right? You will be able to recompute everything 10 times before it will pay off to actually move something anyway. And so the tools and the infrastructure that we have today are completely useless in order to do that optimization. Because all they talk about is minimizing the number of operations. You describe in your program the operations. You can change the number of operations you do. Right? And so that's kind of where all of this is coming from. And that's kind of part of the reason why I find this extremely exciting to work on. And so obviously, I have my favorite guy here. I've been showing this. Anybody who's seen a talk I'm giving, this guy is kind of around for a while with me, because you know, changing the way that software is being written clearly is an insane activity. But I've just recently decided to add another slide to this, which is this one, which should also be familiar, of course, from Arthur C. Clarke, and it fits kind of nicely with the previous slide. In terms of what is or isn't impossible given enough time or enough pressure. And so, you know, the second law is really a bit more applicable. What we're trying to do is really scratch at the impossible, trying to see what it is that we can move out from the impossible space over to the possible side to get things moving. And so in order to do that, we need to use, since we have Arthur C. Clarke, we need to use little blue men. And so looking at these little blue men, you can see it's computing in time. There's a fetch execute loop. Right? So instruction fetch, decode, read from the register file, execute the instruction, read back. You have a cycle. The progress of this guy depends on the clock frequency, on the speed at which this cycle moves. And we've seen that we've reached the limit of how fast we can spin the wheel. However, if we move things in space, it can be very tedious. Very, very hard. The guy has to walk, has to carry the thing over. Really what happens as you parallelize is that you have a multi-core processor. You just have a lot of these guys spinning around. And having now to talk to each other while they're doing it, the faster they turn around, the more difficult it is for them to talk to each other. At some point, you reach a limit here. While in the spatial paradigm, you can imagine a chain that can be millions and millions of these guys who all don't need to know about each other. All they're doing is locally passing something to somebody else. And the structure in which they're passing things around is the structure of your problem. And you have your problem, and as long as that structure scales out, everything is fine. I was inspired in this direction by a master's thesis at MIT in the early 90s, where the students simply set out and said, what if there is an infinite amount of space? How would you compute the problem giving an infinite amount of space on the chip? And say, let's start with that. What is that optimal solution giving infinite space? And then, using origami, and that was the title of the thesis, it was origami circuits, let's fold the optimal solution in infinite space back into the space that we actually have. Right? So that's kind of, from a concept perspective. Now, there is, of course, the connection back to all of the multi-core work. There is OpenSPL, there is CUDA, there are all of these other ways of doing computation. And if you think over the last few years, we've hit the memory wall, we've hit the power wall, we've hit the frequency wall. How many cores are we going to be putting on a chip? Right? Well, we can put on 500 cores. We're going to have 500 threads communicating with each other, all talking to each other, doing stuff. And we debug that. Somebody said something wrong to somebody else. Now you have a communication debugging problem that is infinite. We could have 5,000 cores, 50,000, 500,000. At some point, there's going to be a limit to how many of these cores can all be talking to each other. Because there's a limit to how many of these threads you have. So So dealing with the core wall is one of the purposes here. And so in programming this, you have, of course, the CPU and memory with the fetch execute loop, and you have instructions, write, get instruction, read. And in computing in space, you would have a layout of arithmetic units and a flow of data that flows right through. As a side effect, we now know exactly how long this program is going to execute. We don't need to guess, we don't need to worry about events, we don't need to worry about interrupts, we don't need to worry about any dynamic activity. It's simply a network of arithmetic units, and the data flows in on one side, it flows out to the other side. If I have a gigabyte coming in here, the time it takes for all of this computation here depends on the frequency, let's say 100 megahertz of speed to get things through. You can calculate how long it will take to process 1 gigabyte. And guess what? It does not depend on the number of operations that you have here, right? Or at least to a very, very little extent. It's just a pipeline flush in the beginning. So the number of operations has no connection with the time it takes to compute in this model, which breaks the fundamental principle of computer science, which counts operations in order to figure out how long it takes to compute an algorithm. Right? And so that's something that we need to deal with. And so putting all of these things together, we have this consortium where we have a lot of ideas, but of course, as some of you have found out already, there is no software there yet, there are no tools, there is no infrastructure to support all of this. So we are just slowly starting to put together all of the bits and pieces, and are welcoming anybody who would like to make any contributions. But the basics of all of this is that we are decoupling the control flow and the data flow. The operations exist in space rather than in time. We can customize these operations. We can put them together into kernels in order to be able to manage the collections of different ones and piece them together. And then the data streams through these operations in kernels. We are balancing the transport, so what we want to do is to have everybody busy at all times, because that's what makes most energy efficient computations. And so we are balancing the flow of data through that network, and then all of the resources work all of the time. So what we need now is a programming model and a programming infrastructure to deal with all of this. So here is how that would work. What you simply do is you declare variables, you declare inputs, you declare outputs, and you have expressions in between. So very simple. Moving average example would simply say, well, you take the previous value, the current value, the next value, divide by 3, and you feed it back out again. You get a flow graph like this. Data flows in on the top, it flows out on the bottom. Right? Very simple. Of course, the world is not simple. The world is complicated. The world has loops. The world has dependencies. The world has all kinds of crazy structures that one has to deal with. And so the actual infrastructure has a lot of features in order to deal with this. Given that we have implemented a wide range of applications from sparse matrix algorithms to finite difference, PDE solvers to optimizers, there is a wide range of things. For example, this is an example of an n-body kernel, and clearly there's a dependency that you have to deal with. So now you have to create loops inside of your flow of data. And your scheduling of these loops needs to make sure that there is data in all of the stages. As everything flows, you have to have data everywhere to keep moving through all of these different loops. And so there's an infrastructure that helps you do that. If you have enough data to flow around, there should always be some data that can be at some point at any point in time. And so the job of the programmer then is to make sure that all of the data is where it needs to be and flows through, so that none of the arithmetic units sits idle at any point in time. And so that's what you do with optimization calls. You can optimize the pipelining of these loops, and you can create loops by simply connecting back. So this would be stream offsets where you connect streams together and you create a kind of a buffering system around that. And you need to know, of course, the latency of the loop. Right? Because if you have a loop in a data flow graph, the latency of that loop, the time it takes to go through the loop, is the number of independent things that you need to find, that you can do, while that one data item is going through the data dependency loop. And so you simply need to be computing the number of problems that constitutes the number of stages in that loop. And so the infrastructure helps you to do these kind of things. And then what you finally do is you optimize the whole thing. So you can optimize by figuring out how you use zeros and ones, how you encode your problem on the arithmetic level by looking at range and precision, accuracy, discretization in time, in space, but also discretization of your world in value, meaning what are the values that you have in order to represent. And that's, of course, a mathematical challenge already. Then there's the microarchitecture level, which is kind of more of today's topic here. You have the parallelization on the system level, and then you have the complete system setup, where you need to move data across racks of systems. So in order to move data around efficiently, you need to express or compress data or hold it in a place. And what I just said before is that computing more will not cost you any money. So you could compute a lot more as long as you have less data afterwards to move around. And so here's a kind of theoretical background to transforming data into computation and back again. So how can you take data and instead of moving the data, create computation that will generate that data? And then so Kolmogorov tells us this is of course the equivalent. I need to apologize. This is the equivalent of Shannon's theorem, and Shannon was first, and I know all of that. But I still like Kolmogorov's formulation of the same principle, which is of course the Shannon principle of entropy. Kolmogorov's definition is nicer for us because it says the description of any data is of minimal length if it is a Kolmogorov complexity, meaning that there is a minimal length description and we can compute that minimal length description. And of course, K of S is the computation of that data. And so you would say, well, what are we talking about here? What is this? Well, think of having a language to describe a certain stream of bits or a certain set of numbers. You could just remember all of the numbers, or you could remember a program that generates all of them. You could remember all of the prime numbers, or you could remember just a little program that generates all of these prime numbers. If you know that the numbers are all prime numbers, we have a trick. We know that there is a program and we know we can get them. For a generic stream of numbers, we don't have that. So we have to think a little bit more carefully, and a lot of thought has to be put into how to construct that computation. Now, it gets even worse because we don't know how to find that string or that program that would be minimal. On top of that, we don't even know how to find the optimal language to start thinking about that thing that is impossible to do. So we have an impossible problem on top of an impossible problem. And yet, by understanding a computation, it is possible to do quite well, to get very close to this. And we know we get very close to this. There are people studying these kind of things in information theory and in compression and things like that. And so, for example, if you have a video stream and you have a video encoder, H.264 or something like that, you can compress that video stream to something very small. Imagine you would have the infinite compute power to compress and decompress a video stream going in and out of a chip. Now, of course, today, in order to compress a video stream, you need some serious hardware. Right? You need serious computation. If we assume that computation is free, you could do the entire encoding and decoding of your video stream in and out to memory as you're doing your computation. So you can put an infinite amount of compute to really, really reduce your communication time. And so that's kind of a different way of thinking about this. And of course, for every program, for every problem, the solutions there are a little bit different. I also like to add the following sentence here from 1946, because it just shows that even though John von Neumann built up the idea of a memory hierarchy with all of the caches and big memories and small memories, he really didn't like it. He said, you're forced to recognize. He's not saying, we are happy to announce, right? He is saying, we are forced to recognize that we would have to be building these things and it's going to make our life miserable for the next few hundreds of years. But that's just what we're going to have to do, and let's just get over it. There's another one, which is, of course, Amdahl's law. And we keep being told that you can't accelerate anything with accelerators because Amdahl's law tells us that there's not enough parallelism in these applications. And if you take something out, the rest of the stuff is still going to have to move. Still going to have to compute. Still going to have to do something. Now, if you take what I've said before, and you say, well, with multi-cores, the time to compute task X is really a function of the number of serial operations in the code, right? That's what it says here, right? So the number of serial operations, the ones that you cannot parallelize across multiple cores, these are the ones that will set the time. That's how long it will have to wait, right? In computing in space, the time to compute the problem is now a function of the space on the chip. Not anymore a function of the number of operations. So the more space you have, the less you have to wait. Because the computations that happen at each clock cycle are just a function of how much space you have, because the whole chip is going to work for you on every clock cycle. So what you're now optimizing is how much stuff you can pack inside of that one chip, and growing the chip will make stuff go faster, right? Without needing any parallelism. All of the computations here will be completely dependent on each other. Will be completely serial stuff. But the parallelism arises from pushing a lot of data through that serial stuff. And so it's a different, end up in a different world. And there was actually somebody in the 60s arguing with Amdahl at some famous conferences, and our chairman Mike Flynn, who was right there at the time, has kind of brought us this little quote from the big debate that Dan Slotnick, of course, also a very famous architect of the Iliac computer, had with Amdahl on Amdahl's and then on all of these single processor versus multiprocessor concepts. It says, well, yes, you're going to have to put in a little bit of effort. Because in the absence of wanting to put in some effort, you can't do very much. And so that's kind of where we are stuck. What we are trying to do is, of course, minimize that effort, and that's what really this session is about, minimizing the effort, making this type of technology accessible to software programmers. And so here, this is an example. Instead of showing that example, what I'm going to do is I'm going to switch to a real-life demo. It is almost certain that it will fail, but I'm still going to try. Real demos never work when you want. But here it is. Let's see if I can make it. So this is our programming environment now that runs over the internet. You just need a browser. That's all you need. There's no more need for all kind of complicated technology. If you have a browser, you can program with our environment. We call it Web IDE because it's just on the internet. And you get all kind of cool things. This is an example where you get kind of a dual programming view. So rather than in conventional programming where you look at one file at a time, you're looking at two things. As I said, there is the control flow and the data flow, the split environment. The one side which executes on the CPU, and the other side which executes on the data flow engine. Right? And so you have here an example of just the mean. Actually, there we go. This is a good way to show that demos never work. I would have thought that this would calculate the mean, but somehow this is now showing something else. So we're going to simply go back and reload the project. So we go back and we say, no, give us a new project, and you can choose. Let's just choose Sobel filter. Let's see if we can create that. as I said. No, that was the solution, sorry. This is what I should. Ah, and I need to give it a name. Yes. Okay, so I need to give it a name. Project name, FPL 2014. Create. Yes? There we go. And here we go. Here it is. Not too bad. So here we have a simple CPU level activity. Can't be much simpler than just having a 3-letter function call. You call the data flow engine. What you need to do, you need to send some data in, you get some data out. Right? Not very scary, very easy. There's a stream of data going there, stream of data coming back. On the right side, we're catching that stream of data in an input variable that is an input here, x. And what we do is, maybe I need to push this over here. Simply create the counters that would allow us to decide where we are inside of that environment. At the beginning and at the end of the stream, clearly you can't average 3 numbers. You need to kind of have boundary conditions. And so we can create boundary conditions here. It says, are we within the bounds? Then you divide by 3. You're dividing by 3, otherwise you're dividing by 2 because you just. And then we just divide the sum here by either 2 or 3, and then we get the result. Notice that all of the bits are being computed rather than having an if statement that creates a choice between 2 actions. We just compute all the different possibilities and then select which one we want to. So this is kind of a little example. There's a lot more here. I don't have much time to show all of this, but there would be debug output files. There are graphs. You can view the actual data flow graphs of your computation, and so you get a little picture like that. And you have to imagine the data flow from the top to the bottom. You can view this. There are debug environments as well where you can watch the pachinko machine operate, where you have the little ball kind of flows through, and you can imagine how these things work. And so that's kind of the graphical environment state of the world. Let's go back here. And then there are interfaces. How do the interfaces work? Well, you have to operate and interoperate with the rest of the world. So you have the data flow engines. You have an interface to call each one of these data flow engines, which basically just consists of a file. And then you have higher level interfaces to that. So you could have a application level interface, or you can have an interface to write something into the data flow engine deep into the FPGA, where you want to change one little bit of the FPGA to be something else. And so that's a lower level interface, which is the DFE interface. So you could have something changing inside using the configuration and the DFE block as a whole, or a higher level interface. And the whole thing revolves around actions. So you think of the control code on the left, setting actions. Now an action is a computation that possibly takes a gigabyte, 10 gigabytes of data and does something to it. These are not small actions, but large data actions, where an action could be take these 2 gigabytes, push it through 10,000 arithmetic units, then get it back out on the others. And then the actions get pulled back together and presented to an environment where you can hook in with Python, with Excel, with R, with C++, with MATLAB, and then you can really make the data flow engine work inside of any of these environments, and then make it kind of be callable, interoperate with the data structures here, and then just kind of be part of the environment. The thing that you have as an action is something like this. This is an example of a kernel for finite difference for seismic imaging. Here you would push a few gigabytes through these 4,866 nodes, and you would basically be imaging underground. So this is what would be used by oil companies today to image under the sea or in some on land, kind of with the sensors on the land case, seeing what the layers of Earth are underneath. In order to do that, they run simulations where they push the whole Earth, all of the points that they have in the Earth, through a single simulation step through this whole activity. Generating this optimal graph is of course no fun, and so far we have seen very few people who've tried to suggest that they would like to write the VHDL or Verilog for this. While with our compiler, there's a little add-on, and this is all the code you need to run. This is a whole finite difference computation for seismic imaging based on the partial differential equation that you see on the top, which is described over here in code forms. You could change the PD and compute a different one. You're defining your boundaries for your computation. And you basically get a finite difference solver for these particular input wave fields. These are describing the state of the world, density, elasticity, velocity of the wave field through it. And then a little description of the host code, the code that you need on the CPU to drive all of these things. So this little program generates a full Dataflow implementation for any size machine that you would want to have, fully parallelized, automatically generated in the back. So that programming any number of nodes just becomes a fiddling with this kind of thing. Of course, you can see this is not an interface for engineers. This is an interface for geoscientists, people who actually study the science of doing this. And in the end, you get a simulation that looks like this. This is salt. There is a explosion up on the top. The wave propagates, and from the reflections as the wave hits back up to the surface, the geoscientists can map out and actually find out how this looks like. There are a few slides on doing optimizations on the bit level. One of my favorite pieces of work here from France on figuring out how to compute by having the minimal number of ones in your coefficients of your polynomials, which of course translates on our machines to real performance, to real power savings. You can one-to-one map. If you reduce the number of ones in your number, you save money. If you can have coefficients that have less ones, it runs faster. And so that's kind of a cool thing to do. There's optimizations that one can do everywhere. I'm not going to bore you with some more examples. This is astrochemistry, where we see that as the problem size increases, computing in space scales much better than computing with CPUs. We have a nice study from Imperial College that shows GPU performance here, and as the problem size increases, the Dataflow engine computation performance just goes up through the roof, simply because it has much more DRAM and has much more computational capability in there. There is a whole discussion here that I don't have time for, which is about how much space you need for the computation and how you compare fairly two computers in terms of performance. Clearly, in order to compare two computers, you would have to limit space. You would have to say how much computation can you do within a cubic foot of space, within a certain box. And nobody likes to do that, because that's a very inconvenient comparison. But that's why we are arriving at a different optimization point, because what we say is, given a fixed size box, what is the best you can do? And what is the best we can do with this technology? And it turns out there's some significant advantages there. So it's a box-to-box comparison. You take a box, you take another box, and you say, do whatever you want with your technology, show me how fast it's going to be. And you do the same thing on the other box. Now, there's a lot of topics that I've scratched on, and we figured out that we need to do a lot more here. So Georgi and I, we are going to be teaching a new course at Imperial College on computing in space. And you can see here the layout of lectures. There is a whole range of topics and activities that are mentioned here. And if anyone is interested, we would love to share the material and then have other people join in kind of optimizing the teaching and putting together of these materials. Thank you.
So, since we are kind of reconfiguring, as I said at the beginning, let's have a few questions. We still have time to be done at 5 o'clock. What is the idea, right? So that everybody can go on time for the reception. So, please. Yes.
You seem to be, excuse me, you seem to be describing a sort of two-level split in the control flow remains at the top and then there's a lot of data flow beneath. But actually, if you're worried about power consumption, ultimately you need to have much finer control over the easiness or laziness of that massively parallel data flow driven, especially when there's a lot of data dependent predicates in there. So your graphical applications of the kernels don't have hardly any, except for the boundary conditions, data dependencies in their control flow. But the general programming, it's a two-level split. Again, don't we need to have much more programmer or other input into whether these evaluations are done lazily or eagerly, so that the results are ready, typically keeping all of those units running, as you say.
Well, I think, if I understand correctly, what you're referring to is that programming in the way that I'm proposing here is a lot more effort than programming without it.
Well, actually, I'm saying that the von Neumann programming paradigm that we're so used to does enable us to mix the control flow and data flow together.
Yes.
And that is actually needed sometimes, especially when we need to be able to dictate what is an efficient procedure. Counting a huge other part of running a big part of the program whose result is being discarded is going to be, for the foreseeable future, a stupid thing to do.
Of course, of course. And so that's why there is the control flow part of it, and you can mix and match things. And you decide.
You seem to be saying there's just two levels from the talk. You've got the control flow at the top and the data flow at the bottom, and not finally intermixed.
It is not finally intermixed. It forces you to separate it finally so that you can optimize the activity. The question that this is trying to address is how we can minimize the amount of energy and power and time needed for computation in a production setting. A lot of computation today is not in a production setting. It's not something that runs over and over again in a 24/7 way. And so for computations that don't matter, it is true that this way of computing also is not applicable. This is more of a mechanism to address computations that will happen for the next 10 years, 24/7. And spending a bit more time to finally split the control flow and data flow up front, having programmer input on doing that can have a lot of gains over letting the machine figure it out with a minimal amount of effort over and over again as the program executes. Right? So there's efficiency to be gained from building a factory to make shoes only if you want to make a lot of shoes. Right? And you're not going to make friends with any shoemakers. Right? They're not going to like it. So that's the kind of, and still yet you're going to have to want to build a factory, because if you want to make 1 million shoes, you're not going to have 100 shoemakers just trying to make them very few. Which is not happening.
So you're saying it's for a certain class of
Yes,
computing?
yes. But it's not for a certain class of algorithms, it's not for a certain class of problems, it's for a certain class of production settings. It's for a certain class of environments that you want to run for a very long period of time, and you want to be doing things the best you possibly can.
Supposing you wanted to do a hell of a lot of Java combinations,
Yes.
would you implement your compiler in the massively data flow technology?
I don't know why you would. Why does the world need Java populations. It's not a human need. There is no, I understand we need to find water, I understand we need to explore the space, we need to heal diseases.
Oil, then the seismic usually,
Yes.
you need to record the noise of the driller, you need the seismic by drilling, and you need continuously operation 24 hours, 7 days.
That's right.
Continuously.
That's right.
And if you're having enough computing power, they're deciding just to using the square to 1 kilometer to 100 meters.
Yes.
And we are running then also the same problem.
And you know which programming language they use to do that today? Anybody? Fortran. There we go. It's all written in Fortran. And guess what? There is no Java compilations.
From this area.
There is simply Fortran because it is not necessary. It is not needed in order to do that computation. And that's just how it is, right? Now, it's not exciting, and it may not be the coolest programming language in the world. But when you go to a gas station next time, you're going to say, thank you, Fortran. Because that's what's the oil there for you to put in the car. No Fortran, no oil. Java's not included.
And they're using Java as well for the GUIs.
For the GUIs.
Push buttons.
For the websites as well.
There's websites and there's all kind of other stuff. But there's just different production environments that exist and where different compute technologies make sense.
So, yes, short one, I hope.
Given a certain kernel like a loop, which would in Mencer become a pipeline which
Yes.
Dataflows, that's something which a designer hardware will do anyway when we're doing RTL.
Yes.
So would it be correct to say that what Mencer gives us is an abstraction over something which one would be doing anyway, or is that something else added to the fundamental architecture on the FPGA?
What it does, I like to view it as allowing us scalability. It allows us to build circuits that no VHDL designer could ever design better. Simply scale-wise, because it's too large. And then doing optimizations across the whole circuit that no VHDL designer could formulate. So the environment does global optimizations across thousands and thousands of units, which have been developed based on understanding of the data flowing through the whole thing. So these are not optimizations that work for all circuits, but they have been specifically designed for the particular type of circuits that you get when you design data flow structures. So while the regular CAD tool has amazing set of algorithms, and we all admire all of the great stuff that we have in Synopsys and Cadence synthesis tools, they're very general. What we have is something that's a bit limited to the number of circuits that one can generate, but for the set of circuits that we're generating, we are running ILP solvers and all kind of other optimization algorithms that allow us to scale what I would like to write as a VHDL programmer by hand, but it allows me to scale it to thousands and thousands of units very efficiently. And it does that in not a synthesis fashion, but in a generator fashion. So there are two ways to create circuits. One is synthesis, and the other one is the generator framework, where you generate structures, and you're using the generator principle.
Thank you. So, Oskar is going to be here for the reception. So let's move the other questions to that part, because otherwise we'll never be able to finish at 5. I'm actually already worried. Let's thank Oskar again. As I announced at the beginning, we have a series of short presentations to show you. Yeah, I want all of this. I'm sorry, because my battery is running low. To show you that indeed what Oskar was telling you about is